Hey there, Calc folks, back here with another video in our beginnings of the study of the application of integration. And we've seen that application of integration applied to the velocity function in our understanding of motion in space to produce a displacement. But we can also apply it to the velocity function in a slight variation to calculate the distance traveled by that object over some interval of time. So that is what we're looking at in this particular set of notes. We are going to be looking at, again, the velocity vector, I'm thinking Calc 3. Velocity function describing an object's velocity moving along a linear path, and looking at it. Fix my lights a little bit there. Looking at integrating it to produce distance, and there's a slight variation to that we're going to have to consider here. So that is what I have said here in the introduction. You can kind of read through that. Here's what we're looking at in terms of calculation. Right? Given the velocity vector via t, right? The velocity of an object along a linear path at some time t, right? The distance traveled by the object over values of time t in this closed interval from a to b is given by this calculation here, where you can again see we are integrating from a to b the velocity function. But that velocity, not just that velocity function is part of our integrand, it's the absolute value of the velocity function. Displacement and distance are kind of similar in the sense that you are integrating the velocity function in their calculation. Where they differ slightly with each other, right, is that displacement considers direction of motion in its interpretation and calculation, whereas distance does not. Right? The velocity function here is strictly positive in the distance calculation, meaning we are strictly looking at a change of a description of displacement that is strictly a positive interpretation there. That is ignoring any change in direction in that motion, and is considering just the total distance traveled, whether we're moving towards or away from the origin. Keep in mind that when looking at the velocity function, that when we take its absolute value, that also describes what we call speed of the object. That is the speed of the object. So really what we are integrating in this case, folks, is we are integrating all the infinite speeds that are occurring over this interval of time from A to B. All right? And that's what the next note makes note on, right? We are doing an integral calculation, or a calculation that involves the integration of the speeds over some interval of time. All right? And if we integrate over the speed, we get distance. Now, as for calculating the integral for an absolute value function, there was a bit of notes that was given back to us in the beginning here, back in Calc 1, Chapter 5 material. They talk about calculating the absolute value of a function f by looking at the net area of f of x above the x-axis and calculating it, and taking away from that what would be the net area of f of x below the x-axis. And that would give you the value for, and then certainly we're looking at just f of x, not the absolute value of f of x in this calculation. But what this would give you is the net area calculation seen for the absolute value of f of x. That seems a little tricky. What I tell students instead, all right, is essentially just look at the graph of the absolute value of f of x. It's going to look a lot like the graph of f of x, except every region that used to dip below the x-axis is now going to be flipped above the x-axis as a positive result. So in other words, the calculation of the integral from a to b for f of x dx, the way we're going to approach that is piecewise in its calculation, requiring examining the net area interpretations in the graph for the absolute value of f of x over values of x in this interval from a to b. All right? Can be approached, I should be careful there, most likely piecewise. Not always is it going to be piecewise. If the absolute value of f of x is equivalent to f of x, meaning that f of x really never becomes negative, then they're equivalent in calculation, and you wouldn't have to do a piecewise. All right? But if f of x ever happens to dip to a negative value, you are going to have to break it up into a piecewise understanding. Here's an example. Suppose we were interested in finding the distance traveled by the object whose velocity is described by 4 minus 2t meters per second. And we're interested in the distance traveled over this interval of time from 0 to 5 seconds. Let's say that here. All right? Well, that distance traveled will be the definite integral from 0 to 5 for the absolute value of 4 minus 2t. Well, what does the absolute value of 4 minus 2t looks like is a lot like this, except anywhere 4 minus 2t dips below the x-axis, that region is going to be revolved and reflected above the x-axis with the use of the absolute value symbol. So graphically, what we see happening for the absolute value of 4 minus 2t on this interval from 0 to 5 is it looks something like this. And the net area we're interested in calculating is the net area seen in this illustration. This upper bound on this region, this V shape to it, that is defined by the absolute value of 4 minus 2t. Via t, 4 minus 2t, would actually be the line that has a y-intercept of 4 and a slope of negative 2 that would actually begin dipping down here below the x-axis, or the horizontal axis, after the point in time of t where t equals 2. But all this region that used to be below now gets reflected above this horizontal axis because of the absolute value in our interpretation. So the net area we're actually going to calculate from this calculation is going to be the net area seen in these two regions of this graph. The net area seen in this region added to the net area seen in this region. And we got to approach that piecewise because the function defining that net area is different from here to here. It changes. It's related to this one, but it's the opposite of what we see over here. This is 4 minus 2t. What's the opposite of 4 minus 2t? Well, that's 2t minus 4. That's what describes this side, upper bound. All right? So when we go to approach this calculation for absolute value, note from the graph the following piecewise calculation can be performed to calculate this illustrated net area. All right? The definite integral from 0 to 5 for the absolute value of 4 minus 2t is equivalent to the area, or the net area, seen between 0 and 2 for 4 minus 2t. That's this little region of space here for values of t from 0 to 2. And then this space here for values of t from 2 to 5 describes the other half of this net area summarized in the absolute value. But the function defining the upper bound on that space is the opposite of what we see for 4 minus 2t. The opposite of that is 2t minus 4. All right? I do make note of that opposite behavior here. All right? Note the second term in the piecewise calculation exhibits the net area trapped between the x-axis and the curve described by the opposite of via t over t. The value given by the opposite of via t is the opposite of 4 minus 2t, which is 2t minus 4. All right? So if we just jump into the calculation now, and think about what this will tell us for the distance, if I do those two separate definite integral calculations, this first integral's definite integral produces 4t minus t squared evaluated from 0 to 2, which is essentially 4 minus 0, or just the value of 4. The second integration in this piecewise calculation is t squared minus 4t, which is evaluated from 2 to 5, which is 5 minus negative 4 in value, which simplifies to 9. So this is 4 plus 9, or 13 meters in distance. An object whose velocity is described by 4 minus 2t, all right? If it happens, well, the distance it travels over time, t, in the interval from 0 to 5, is 13 meters in distance. It's this 13 meters we calculate down below here. I do approach it with the understanding that I'm calculating the absolute value of v at t, but to approach the absolute value calculation, I do want to sketch out its visual representation so that I can break this up and approach it piecewise. And what we see in the piecewise calculation is you will have the integral over the regions that are above for your function v at t, plus the integral for the opposite of the regions that would fall below the x-axis for v at t. The absolute value is having us look at the opposite of those, taking the negatives and making them positive. It's taking the negative of those negative v at t's and giving us back the positive result, 2t minus 4, for values of t from 2 to 5. For instance, 3. 3 times 2 is 6. 6 minus 4 is 2. 2 is bigger than 0 versus with the negative 2 you would have if you didn't take the opposite there. All right? So, folks, that is distance traveled. It is a calculation that also involves the velocity function v at t, but you are integrating from a to b, that interval, over that interval of time from a to b, the actual absolute value of that velocity function. If you don't put the absolute value around it, folks, you get displacement. We don't want necessarily displacement. Displacement considers where we started and where we ended and what was the total change in position from where we started to where we ended. Now, from where we started to where we ended, we could have moved back and forth quite a few times. We could have covered quite a distance, right? Whereas the displacement would just be this small little portion here. That distance would be all that back and forth in calculation. So they are different. And the way we calculate that difference is with that absolute value of the velocity function, folks. All right? Oh, what did I do there? I need to do that. I'll click over here and do this. All right? So, folks, that's another quick video here in the the application of integration, looking at motion in space in that very first section of Chapter 6. Like I said, that was kind of a beefy section. It has what I've narrowed down about 4 topics of material in it, and I've slowly gotten these videos out to you folks over these 4 topics. So that wraps up 6.1. 6.2 is a little quicker. That's our other topic for the week. I'll be jumping on that video here shortly. Let me get this uploaded and off to you folks so you can get to watch that this evening, I hope. But I'll be back with area between 2 curves in my next video. Moving on in our sections of material. So, folks, I hope you're hanging in there. It was good to see you in class today. I hope to see you tomorrow. Look for this video. Look for some more videos. Keep on top of all this, and we'll talk then. See ya.